Now, at the page 523 of the textbook, they give you this equation, this one right here, this expression 30x plus 18. They ask you to find the prime factorization on that. Raise your hand if you know what prime factorization would be. No one remembers what prime factoring? Okay, can raise your hand if you tell me what a prime number is.
Number that can't be multiplied into.
The number whose only factors are 1 and itself. So working with those prime numbers, you're looking for numbers, only prime numbers that when multiplied are going to give you that number here. So looking at 30, they already told you got a prime factor of 2. The next one would be, well, let's see, 2 times 5 would give you 10, right? 10 goes into 30 how many times? 3 times. So 2 times 5 times 3 is going to end up giving you 30. Now, you could work with a factoring tree to work this out. We could work with other ways of finding it. General thing is, if you do have the prime factors worked out, you can work that. You do the same thing for the 18. Well, 2 times 9 is 18, right? But they got 2 spots here because 9 is not prime. What 2 numbers are prime that multiply to give you 9? 3 and 3, right? 3 and 3 will give you the 9. So what they've done is that we broke down those numbers to their prime factors. And then in the next step, they ask you to circle the common factors. I see a common factor of 3 and 2. Notice how I did not circle this other 3. Why did I not circle that 3? Isn't it in common with the other one there?
It doesn't have another 3 to go with it.
Yeah, it not only has to be in common, it has to be just a one time. There's a one, shows up only once here, there's not a second 3, so I'm only going to have the 1, 3 from that one. Okay, so, since I only have the 1, 3 and the 1, 2, that 2 and 3 are going to become part of my GCF. Now, what's being done with those 2 and the 3 in here? They're being multiplied. So when I find that GCF, it's not going to be 2 and 3, it's going to be 2 times 3, which is what? 6. What's that leave over here? If I got to take the 2 and the 3 away, what am I left with? 5x, which would be what goes in here, of 5. The x is already written there for you. What's left over here? The 2 and the 3, we're going to take those out for the GCF. What's left? Just a 3. So we're going to put a 3 in here. And this should be filling in spots, I believe it's A, B, C, and A, B, and C. The one middle spot has, all of this just rewritten so you can circle it. So any questions on that first part there? Yes?
I didn't get what you did for the second.
How I got from here to here?
Yeah.
Okay. Do you understand why I circled these things? Why I circled these and these? Okay. This 2 and this 3 form the GCF. This is the GCF. I've pulled that factor out. What we're doing is kind of a reverse distributive property. I found that this first term, has a factor of 6, right? And the second term has a factor of 6. So I pulled the 6 out of these 2 numbers, and then what was left was just the 5x for this term and the 3 for this term. Does that make sense? So I've pulled out that GCF. I determined what the GCF was with the circling, and then I pulled it out and wrote it separately here with what's left here. I've kind of divided both. If I go in here and if I divide 30x by 6, oops, and then I divide 18 by 6, I would get the 5x for 30x divided by 6 is 5x. 18 divided by 6 gives me the 3. Does that make sense? Okay. Yes?
I have 2 questions. The first one is I didn't get the worksheet like after I passed them all out, and the second one is on this. Like, what's the difference like for B and A? Like they're the same problem, but what do you like put for each?
In your textbook, they didn't, I didn't write it twice up here, but the textbook they wrote it twice, because they basically ask you to copy it and then circle it, so you don't circle the original. So it's basically the same thing. Okay? As far as the bell ringer sheet, you check to see if you didn't turn it in, I didn't grade it, so I didn't get it turned back. So you may want to check your binder, see if you have it in there.
Okay.
All right, now, one question. Will you get a completely factored expression if you factor out a common factor that is not the GCF? Raise your hand if you have an answer for that one. Eve? No, you would not. That is correct. Let's see. Can anybody explain why? Well, if you don't factor out the GCF, then there would still be a common factor left between the numbers. See, if I were to pull out the 2 only from here, that would leave my expression as 2 times 15x plus 9. Does this expression here, does this expression equal this expression? If I do the 15 times 2 and the 9 times 2, I do end up getting the 30x plus 18. But is this completely factored? No, because there's still a common factor between the 15 and the 9 of what? 3. So it wouldn't be completely factored unless you factor out the GCF. So will you get a completely factored expression if you factor out a common factor that is not the GCF? No. There would still be a common factor left to factor out. Might be a little bit wordier than what the textbook has, but it's the way I would write it. Okay, is the expression 2, 3x minus 4x completely factored? Raise your hand if you can tell me, is this expression completely factored? Holly?
Yes.
Don't sound very confident in that. Yeah. Who agrees with her? No one agrees with her, so who disagrees with her? Eve, why do you think it's not completely factored?
Because it didn't distribute yet. Oh, wait a second.
We don't have to distribute. When we're factoring, we're actually doing that reverse distributing. Yes?
Well, I think it's factored.
You think it's factored, so you agree with Holly. 4 is not a prime number. Sometimes, yeah, the factor, yeah, when we were finished up here, that 5 and the 3, those were prime numbers, so that did make sense. But what's left over is not necessarily going to be a prime number. The 6, is that a prime number? No. But was that the factor, was that the GCF? Yes. Problem here is that there is still a common factor in here. What factor do both 3x and 4x have in common? They both have an x. You see, they both have an x.
Wait, so is it factored?
It's not factored completely. It's factored, but not factored completely because there's still the common factor of x. So the answer here is no. There is still the common factor of x. I do apologize for the handwriting. I'm not very good with electronics writing here. So that is C-O. Yeah. All right, now, if you were to factor this completely, you would end up getting 2 times, you have to factor out the x, which would leave a 3 minus 4 inside the parentheses. You factor out the x, you get 2x, 3 minus 4, which could actually all simplify down to negative 2x in the end. Because 3 minus 4 is negative 1, and I've got that. So on page 524 there, they've got this question after the example there. And what they're essentially saying here is if you had something like 3x to the 12 and 7x to the third. And you went to find the GCF here. Well, is there any common factor between 3 and 7? No. Is there a common factor between x to the 12th and x to the third? Each one of those x's is a common factor, but how many of them are common? 3. Because there's 3 here, 3 x's here, and there's 3 x's there, but out beyond, there's a lot more here, right? So even though there's a lot more here, because of the 3 here, there's only 3 in common between the two. So whenever you have a variable to an exponent within two terms that you're trying to find the GCF of, if it's the same variable, the GCF is going to have the lower of the two exponents. So in two terms, if two terms contain what power will the variable be raised in the GCF? The GCF will, not very good, Alan, will have the variable raised to the lower exponent value, which in this case would be the 3. Okay. So anytime you have two variables and the same variable in two terms and you're trying to find that GCF, the lower exponent will always be the GCF of the two. So that in this case, the GCF was x to the third. So if I go to factor this one, there's nothing I can do. There's nothing I can do with a 3. There's nothing I can do with a 7. But I can factor out that x to the third. So this becomes x to the third, 3x. Well, there was to the 12th, but I've taken away 3 of them, right? So it's going to be x to the 9th plus 7, and there's not going to be any, because x to the third is going to be taken out away from there, so it's just factored out that. The GCF turned it out to be that x to that lower exponent value. It will always be the lower one. Does that make sense? All right. So the second question on that page says, can the GCF of two positive numbers be greater than both numbers? Can you have a GCF that's greater than the other numbers that we're trying to find the GCF of? Is that possible, Jonathan?
No, actually not.
No.
Also made exertion.
I think I already sent somebody.
Yeah, me.
He's back.
Can I go?
But, yeah, so. All right, so the answer here is indeed no. The largest factor. This is not very neat. Let me see if I can. The largest factor of any number is itself. So if the largest number of any number is itself, the largest factor of any number is itself, it can only be as large as one of the numbers. Now, if we're talking about negatives, then things could be larger because one could be a negative and positive and all that. But as far as the largest factor, if any, no, it cannot. Okay, we are asked to find the GCF of these 4 problems on the bottom of page 524 in our textbook. Looking here at the 18 and the 27, what's the GCF of the numbers there? 9. What's the GCF of g squared and g to the 5th? G squared, the lower of the two exponents. So that is the GCF of those two terms. Okay, I found, how did I do that? Found there's a common factor between 18 and 27. Knowing the factors in my head, you can break it down to the prime factors, or you can break it down to regular factors, but we know, if you know the numbers well enough, you know that 2 times 9 is 18 and 3 times 9 is 27. So they both have a factor of 9. And there's not going to be any larger factor than the 9 between them. All right, so we got the GCF of 9, and then we found the GCF of these two. Well, they both have the same variable, so the lower of the two exponents, if they have the same variable, the lower of the two exponents will be the GCF exponent. Okay, so number 6, is there a common factor between 16 and 9? Well, the only common factor there is 1. Now, I can't quite say that's the answer. Yeah, we still have to look at the A and the B, but those are two different variables, right? The two different variables, there's definitely nothing in common with those variables, so it's just plain 1. That's how we do end up with just plain 1 as the GCF here. It wouldn't necessarily be none, because there is a common factor of 1. Is that going to help you? In some cases, yes. Some cases, no. All right. Jonathan? No, it's after 4 o'clock. All right, number 7. For number 7, we have 15 and 45. What's the GCF of those two numbers? 15. What's the GCF of the G to the 4 and the G to the 3?
The answer would be 1.
G to the 3rd. Okay. For number 6, the answer was 1. Number 8, is there a common factor between 9 and 16? No. There's no common factor between 9 and 16. The numbers itself, just the numbers. Between just the numbers, there's no common factor. Okay, so is there a common factor between 9 and 16? Just the numbers. No, we already established that in number 6. What about the A and B and the B and C? Is there a common factor there? Well, they both have B, right? So there is a common factor of B. It's not B squared, because we're not multiplying those two. It's a common factor of just the B. Okay, so the common factor here is just the B, and that's it. You could say 1B, but putting a 1 in front of the variable doesn't mean much, right, Jonathan?
Yes, sir.
All right. So to answer these questions on the bottom of the page of 525, we're going to figure out what the GCF is of each of the terms. Between this term and this term, what's the GCF? And then we're going to divide both terms by that GCF so that we can figure out what the new binomial in this case would be. All right, so what is the GCF? Well, there's a negative. Both of these are negative, right?
So you put 1 over?
So I would say that we have a negative as a common factor there. What's the GCF of negative 28 and negative 12?
Negative 4.
So it would be a 4. It would be negative. All right. And we have a y squared and a y to the 5th. So the GCF would be y squared. Now, what's left here, we're going to divide both of these by that negative 4y squared. We're going to take those out. Negative over a negative will give you a positive. 28 divided by 4 gives you a 7. Y squared divided by y squared, well, they cancel each other out, so you're left with just the 7 there. Y squared divided by y squared. If I'm dividing these two here, dividing this term by negative 4y squared, negative divided by negative is a positive. 28 divided by 4 gives me the 7. Y squared divided by y squared is 1, but 1 times 7 would just be 7. So the y disappears from that term. But over here, 12 divided by 4 is going to give me a 3, and it's positive because of negative divided by negative. Then we have y to the 5th divided by y squared. When you have like bases being divided, what do you do with the exponents? You got to subtract. So the 5 minus the 2 is a 3. So you end up with y to the 3rd power there. Or cubed, yes. What common factor do you see between all 3 of these terms, the coefficients of these terms? What common factor do you see? 2. Now, there's a positive here and a negative here and a positive there. We're just going to, when it's not all negative, we're just going to work with positive for the common factor. So we're going to pull out that 2. That means we are going to end up dividing each of these by 2. All right, so 8 divided by 2 is going to give me a 4. Whoops. Well, is there any other, wait, is there a common factor with the x's here? I forgot about that. Is there a common factor with the x's?
No.
Yes?
Yeah, there's an x in all 3 terms, right? What's the lowest exponent? 2. So they all share an x to the 2. So we're not dividing by just 2. We're going to be dividing by 2x squared. So x to the 4th divided by x squared, we subtract the exponents. 4 minus 2 gives me 2. 4 divided by 2 is 2. X cubed divided by x squared is going to be x to the 1, which is just plain x. Negative 2 divided by 2 is going to be negative 1. And x squared divided by x squared is also 1, so you just get a 1 for that last term there. That's how we factor. And over here I should have the x squared because that's the GCF on the outside. To double check it, as you saw in the example problems, you would distribute backwards. If you do distribute, 2x squared times 4x squared gives you 8x to the 4th. 2x squared times 2x would give you 4x to the 3rd. 2x squared times negative 1 will give you negative 2x squared, which would give you that same final answer in the background. So we factored out that common factor, that GCF, and we. All right, to factor these, we've got, notice how this binomial and this binomial are the same, aren't they? This has a coefficient, and that binomial is 7x. This has a coefficient of an understood 1. Think about this. If I temporarily say that y is equal to 2x plus 3, this would be same as saying 7xy plus y. And the common factor between these two terms, the common factor between this term and this term would be a common factor of y. So if I factor that y out, this would then become y times 7x plus 1. Okay, I ran out of time in class here, but I did want to at least put the answers onto this video here. You'll see that the answer for number 13 is here. The answer for number 15 is here. The keys to remember here is that t plus 6 is the same thing as 6 plus t, because addition is commutative. So these two are a common factor between these two terms. So that's why we're able to pull out a t plus 6 separately. Here, common factor is x plus 2. Number 14 in the textbook I didn't put in here because number 14, there is no common binomial like there is here. So number 14 cannot be factored any further, whereas these can.